So I have noted down certain questions from exercise 8.1. In fact, all the questions. Uh, in some cases, I will be giving some hints, and the other questions which I have already discussed, I will skip. Okay. So this was the first question from exercise 8.1. The proof that this converges. We need to prove that this is a convergent series. Okay. So you know that this series. This is a summation n equals to 0 to infinity and then 9 divided by 10 to the power n. And this can be written as, you know, there is a, you can see here, there is no power on 9. So you can very much write like this, 9 n equals to 0 to infinity and then 1 to the power 1 over 10 to the power n. Fine. So this goes like this. When n is 0, so this becomes 1. So the first term is 1. Or you can write 10 to the power 0, 1 over 10 to the power 0, then 10, then 10 square, then and so on, like this. And this is, this is GP. Already, this is GP with the common ratio is 1 over 10. No? So with this, you can compute the sum of this. And of course, this is convergent. Fine. This is convergent. And one more thing you can say, this is a convergent and you can find the sum. What will be the sum of this? 9 times. The first term is A. You know the formula for GP of sum of infinite terms, A over 1 minus R. No? So if R is between 0 and 1, then we can use this formula for infinite term. A is 1. So 1 over 1 minus 1 over 10. So this you can simplify and find the sum. And to claim that this is convergent, because this has finite sum, so of course this is convergent. Okay, a series is convergent if it has finite sum. So this is a way how we can claim that this is a convergent. Otherwise, you can find Sn. For that, you have some formula like this, something like this, no? Something like this. You have formula, and then you make this sequence, find the sum, and then you can check the convergence of this Sn. And then second part, what does this tell you about infinite non-terminating decimal? This, and you must be familiar with this term in earlier classes. This is 0.999 and this is repeating all the way 99. This is repeating. So this you can write as sum, this 1.9 and then a 0.09, then 0.00 and 9 and then and so on. So you can write this term as 9.9 is there. So 9 by 10 and then you can write it 9 by 100. 100 you can write 10 to the power 2 and plus dot 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 and so on you can write. Fine. So this is a similar, this is the series you are going to get. This is, you can write summation 9 upon 10 to the power n, where n start from 1 to infinity. So you can find the sum in a similar way. And this sum would be like this. Okay. So second question is that to find the sum of each of the following. So this is a similar thing what we have discussed. Okay. So this A part is that you can see 0.0 and 1, then 0, 1, then 0, 1 repeating. You can write it as 0.01 and then plus 0.0 and 0. Okay, fine. You are writing as sum. So this term I have written here, and then I need to produce this much also. So this we can produce by writing 2 0 and then another 0, then 1, then 3 0 and then 1. Okay. and then and so on. So we can write like this, this we can write 10 to the power 1 and below decimal you have to write 1 and then 0. So this you should divide by 1 divide by 100. So this is 10 to the power 2, and then this is plus. Okay, this is plus. I guess 0. Okay, this is 0.01, and then we need a 0.00, and then how much? 0 0, then 0, another 1. No? So 0 1 like this. So once we are adding 1 0 and then 1 and then 0. Okay, okay, we are getting the same thing. No? We are getting the same thing. So this term is going to be 10 to the power, I guess 3. 10 to the 1 and 10 to the power 3. No. Is it okay?
10 to the power 4.
10 to the power 4.
Yeah, 10 to the power 4. Yes, yes, yes. 10 to the power 4. Yeah, 1 0 0 0 and 0. No? Okay, 10 to the power 4. Yes, 10 to the power 4. So like this. So this is another GP, and you can compute the sum easily. Fine. What you can do about this? This is repeating. And this 0.9876, 9876, 9876 repeating together all the way. So you can write this also. You can consider first one, like the B part, 9876. Na? So first, and then it will repeat all the way. So you can write it 9876 divided by 10 to the power 4, and then plus 9876 divided by 10 to the power 8, and dot 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 like this. And then you can find out the general term, and after that you have to compute the sum of this geometric series. Fine. You know this one. This is alternating series. No? This is alternating series. And of course, we have not discussed until now when we were discussing this chapter. So there was no concept of alternating series. But with the help of alternating series also, we can solve this one. We can solve this one. We can solve this one by using alternating series. Of course, every term is decreasing. And as n tends to 0, the nth term is going to be 0, limit of nth term. So this is using Leibniz test. This is convergent. Fine. But thing is that we need to find the sum. Leibniz test tells that this is convergent or not. But when it comes about finding the sum, so we need to think something. Okay. Something more about this. So the series, what the series have been given to us is which series is this one? 1 minus 1 by 2 plus I think 1 by 4, then 1 minus like this. Okay. So you know that if a series is convergent, then insertion and removal of bracket doesn't says the nature of series. So, you know, by Leibniz test, this is convergent. So we can insert bracket like this. Okay. So this first term is 1 by 2, and then second term is 1 by 8, then third term is 1 by 32 or something here. Of course, you can write it in the power of 2. No? And then you can use the GP formula, geometric progression formula. And you can then get the first term is 1 by 2, and then common ratio comes to be 1 by 4, I guess. Yeah, 1 by 4. So this is going to be going to give us 2 by 3. So this is the answer of this one. And a similar thing you can do with this also. Okay. Now let us come on this one. E 3 to the power 4. Sorry, the series given is 3 to the power n and 4 to the power n divided by 5 to the power n. And the sum is starting from 0. We need to take care of this when it comes about to finding out the sum. Actually, of course, the nature will not change if some finite number of terms is removed or added. Current nature will not change, but some will change. Okay, so this we can write summation un n equals to 0 to infinity. So un is what? 3 to the power n plus 4 to the power n divided by 5 to the power n. So we can write 3 to the power n divided by 5 to the power n plus 4 to the power n divided by 5 to the power n. And this all the way we can write 3 by 5 to the power n and then 4 by 5 to the power n. Okay, so this is un. This is un in our case. Okay, so now the series becomes, this is sum of two series, 3 to the power 5 to the power n equals to 0 to infinity plus summation 4 by 5 to the power n equals to 0 to infinity. And as it is clear that both are in GP, and the common ratio, the ratio is less than 1. 4 by 5 is always less than 1. Okay. So in this case, the sum, what would be the sum? A, the first term, n equals to 0. No, n equals to 0. So this becomes 1. The first term is going to be 1. So A, that is 1. The sum of this is 1. A divided by, what is the formula? A divided by 1 minus R. So 1 minus R is going to be 3 by 5. And then in this case also A is 1. And then 1 minus 4 by 5. And then we can find the sum of these. This is going to be 1 times 1 divided by 5 minus 3. This is 5 minus 3, that is 2. 5 by 2, I guess. 5 by 2 and plus 5 by 2 and then plus this one is 5. Yeah, 5 is 5. So 5 into 2, 10 plus 5, 15 by 2. So this is sum. So in this case here, which one we did? This one, I guess. Yeah, this one. This is 3 to the power n, 5 to the. Here you see this one. This term is 5 by 4 to the power n. And this term is plus 3 by 4 to the power n. Of course, this common ratio is less than 1, but this common ratio is greater than 1. This will give us convergence series. This will give us geometric series. You know, this geometric series x to the power n is convergent if and only if, do you remember? Mod of x is less than 1. Absolute value of x is less than 1. So this is divergent. This part makes this divergent. So the sum of this series is going to be how much? Anyone? Infinity. This is another alternating kind of series. So you can just do as this one, C part and this part. Okay. This part, this is also very simple question. I'm leaving it. In fact, this part, H part, if it is convergent, then we can think of the sum. No, the n upon 2n plus 3, n upon 2n plus 3, summation n divided by 2n plus 3. So here un is n divided by 2n plus 3. No? So necessary condition is limit should be 0. So this is infinity upon infinity. So let us use L'Hopital rule as limit n tends to infinity. Differentiate this, we get 1, and differentiate this, we get 2. So this is going to be 1 by 2. This is non-zero. So series is not convergent. Series is not convergent. So we need not to find the sum. Of course, sum is going to be then infinity. here this one sine n pi, summation sine n pi. So here un equals to n pi sine n pi. Sorry, sine n pi. Sine n pi. So when n is 0, then sine 0 is 0, you know, when this what we say that n is 1, then sine pi. Value of sine pi is what? Sine pi when n is 1, sine pi, what is the value of this? Are you getting my voice?
0.
Please do respond. Otherwise, it would be difficult for me also. And sine 2 pi? Sine 3 pi?
0, sir.
Every term will be 0? Or what?
Yes, sir.
Sure? Are you sure about this?
Yes, sir.
Okay. Then every term is 0. So in this case, this series becomes 0 plus 0 plus 0 plus dot dot dot. So sum is ultimately 0. No? So this is convergent. No? This is convergent. But on the other hand, if you see this sine n pi by 2, this one, sine n pi by 2. So the last part of the question number 2, sine n pi by 2. So not all terms are 0, no? When n is 0, then this value becomes 0. When n is 1, then this becomes 1. When n is 2, so 2 pi by 2, this becomes 0. When n is 3, then it again becomes 1. So this is ultimately, here un is sine n pi by 2. This doesn't converge to 0, no? So if the limit is not 0, so this implies that the series is not convergent. Series is not convergent. Then we have third question. Prove that this diverges and this also diverges. Why? In the first case, cos nx. Now here un is cos nx, and this doesn't converge to 0. In the second case, sine nx, and here also vn. If I say vn, this vn is sine nx, and this doesn't converge to 0 because this depends on value of x. If x is a multiple of pi, just like x equals to some n pi kind of thing, so in that case, every term of this will be 0. Nah. So in that case, this will be convergent. Fine. And this is what here written. Unless pi is an integral multiple of x is an integral multiple of pi. So this will change value as a sequence. This is not going to converge to 0. This is also not going to converge to 0. So none of them is convergent. This tail, M tail, I have already defined and we have discussed it in plenty, this kind of thing. So I'm leaving it. Okay. This also we have discussed, altering or deleting the finite number of terms in infinite series doesn't affect the convergence of series. And this you can relate from here. You just remove first m minus 1 terms from the series. Okay. And then you know that tail decides, this tail decide m tail. M tail decides the nature of series. So if you are removing this, that's what here it is mentioned. If we are adding, altering, or deleting finite number of terms. So if we are writing, there may be finite number of positive terms, negative terms, or some negatives, some positives also. So this actually doesn't affect the nature of series. Of course, this affect the sum in case it is a convergent. In case it is divergent, then of course this sum is going to be infinity only. So if you infinity you are adding this much term, doesn't affect. Infinity plus finite number of terms, finite value is going to be infinity only. So from here, because tail, you know, and then later on this becomes this one. This gives us what? Cauchy criteria on convergence, no? So this you must be knowing. If you remember, I equals to.
Yes, sir.
Yeah, please. Hello.
Sir, the screen is not working on sine phi.
Sorry. This one.
सर स्क्रीन रुक गई है साइन पाई पे.
Okay, 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 okay. Screen is not. Okay. Screen is not coming. Okay, let me again try. Now, are you able to see? I'm scrolling up and down.
Yes, sir.
Yes, sir.
It is working.
Yes, sir. Now working.
Okay.
Yes, sir.
Okay. Okay. Please let me know if there is any technical issue. No?
Okay.
So you know that M tail of any series is defined in this form. So in M tail, we ignore the first of some finite number of terms because the nature of series is defined is totally determined by the tail, M tail of the series. No? So we have discussed this you know, for given epsilon greater than 0, if this is less than epsilon, so the series is convergent. No? For some m is greater than or equals to n naught, where n naught some natural number. No? So this totally depends on the tail. So if we are removing it or we are adding some finite number of, doesn't affect the nature of series. So with the help of this M tail, you can prove this one. And of course, we have discussed it in the class also. And then sixth question is that prove that every sequence is the sequence of partial sums of series. Every sequence, they are talking about every sequence. So if we have x, they are writing xk, so k is equals to, suppose we are writing from 1 to infinity or 0 to infinity. No? Then we define s1. Here they are writing a1. No? So okay, let us write a1. Let's just write a1. So a1 is s1, a2 is s1 plus s2, a3 is s1 plus s2 plus s3, and so on. And an in general, we can write s1 plus s2 plus dot 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 plus sn. Here not sn but xk. Please forgive me for this xk, because we have taken the series with terms. Sorry, where is pen? Here. So x1 plus x2, x1 plus x2 plus x3, x1 plus x2, and so on, and xn. So all these terms we have added, and then nature of this series is totally determined by the sequence an, this sequence of partial sums. So for every corresponding to every series, we have we can find this kind of partial sum of series sequence and corresponding to this. Fine. And conversely, also no every sequence. Okay, fine. So every term we can write, we can break them into, suppose the first term is of, suppose we have been given this sequence, so we can write the first term as x1, the first term of this series, and then a2, the second term of this sequence, we can write as a sum of the first and then second one. Okay, so this we can continue like this. This is a telescopic series. We have done it already. No? Okay. This one summation n equals to 1 to infinity, and this is bn and vn plus 1. So if we expand it, so v1 the first term, the second term is v2 plus then v2 minus v3 plus v3, and we continue, and the last term is going to be bn plus 1. So these two positive and negative makes together 0. So we ultimately will get b1 minus bn plus 1. Fine. So this is sum of this series. This is sum of this series. And when we take the limit, because this is in fact this implies that this is Sn. This is Sn. This is Sn. SOPS. SOPS. So limit of Sn is equals to limit of b1 minus bn plus 1. This is b1 is some constant. So b1 minus limit bn plus 1. So once we have this this kind of formulation, so this limit exists if and only if bn, this sequence bn is convergent. Okay, so if its limit is bn, if I may write bn converges to b or bn plus 1 converges to b, both are the same thing. Okay, so here they are writing bn converges to b. So here in this place they are writing b1 minus capital B. So this was a telescopic series. And this question we have done already in the class using partial fraction n plus 1. So un is 1 upon n times n plus 1. How we can write 1 upon n minus n 1 upon n minus 1. So this is nothing but telescopic series. Fine. This is telescopic series, and then Sn is 1 minus n equals to 1. So b1, this is the sum of, we are using this one, bn minus bn plus 1. So here this is bn and then bn plus 1. So the sum of n terms, first n terms is going to be this. And the limit when we compute of Sn, this is going to be 1. Okay. Here another question we have. So here also un equals to 1 upon n square plus 5n plus 6. So just let me know what would be the factorization of this. How we can write n plus 2 and n plus 3. And then you make the partial fraction. What we should write here, n plus 3 or n plus 2, n plus 2, let us write here n plus 3. So once it will go here, and I think it is okay. No? This is okay. So you can again, you can start this, you can make it use the telescopic series kind of thing, and or other way around also, because the terms are positive, not only this. Okay, terms are positive. But you can, of course, you can use the comparison test or ratio test also here. But using that, you can also only find the nature of. You cannot find the sum. So prove that this convergence and find its sum. So for sum, if at all we need to find the sum, we need to make SOPs. Wherever they are needed sum, we need to look for SOPs. Some sequence of partial sums. Here in this also, this we can write as telescopic series x plus n minus x plus n plus 1. This is a partial fraction of this one. And then we can then you can find the sum Sn, the first term of this what is 1 plus x minus, and this is x plus n plus 1. Okay, so you know that limit of this is 0, nah? And then we are left with this one. So sum of this going to be 1 upon 1 plus x. Are you getting what I'm telling? In case of telescopic series, the sum is bn b1 minus bn plus 1. So we need to take care of this. Or you can write some terms, four to 6 terms, and then you will get an idea which terms are getting cancelled, and what we are going to left with at the end. And this also un is, so they need use method of telescopic series to find. Now they are telling that to find. It means you have to find the sum. No, you have to find the sum. So n square plus 2n. We can write this n plus 2 and then use partial fraction and then find it out. This is also similar kind of thing. You can do it. This any series can be written as this. We have done in the class already done. Telescopic series, any series can be written as in terms of telescopic series. This we have done already. Or you can refer the book. You can refer the book where they have written. Let me show you where it is written. This one telescopic series. This one is telescopic series. So like this. No, like this. Okay. Or you can refer the book. I have given the details of the same in the notes. The 14th question is that an is an arbitrary sequence of positive real numbers. Find a formula for nth partial sum of the series. This one. Okay. For what sequence an does this series converge? In case of convergence, what is the sum of the given series? So everything will be clear once we know the sum of this series. So thus given the given series is ln natural log an divided by an plus 1. Okay, so here un is log an divided by an plus 1, and you know that this is log an minus log an plus 1. We can very much write like this. And when it comes to find out the sum, we will refer SOPs, partial sums. Na? We will refer this one. So this one first term is log a1 minus log a2. The second term is going to be plus log a2 minus log a3 plus log a3 minus log a4, and this will continue, So an minus log, this is log an minus log a n plus 1. So in between terms will get cancelled. So we are left with log a1 minus log an plus 1. This is the sum here. And then we know that this we can also write log a1 divided by log an plus 1. So this is going to be the SOPS. No, this is going to be SOPS. So once we need to find the limit of this Sn. So limit of this log a1 minus limit log an plus 1. So this is because there is no n. So log a1, this is free from n. And this we can write limit log an plus 1. So if this converges, then this also converges, Sn also converges, and therefore this series will be convergent in that case. No. So for hot sequences An does this series converge. So any answer from your side? यहाँ पे कैसा sequence ले so that कि ये converge कर जाए? What kind of sequence we can choose? We need to choose such that An such that it has finite value. This has finite value. No? Hello. Are you able to get my? Are you getting my voice? Yes. Tell me then. Tell me. I'm waiting for your answer. You can think of them. No? When you can tell that the limit of An is finite. When it is finite, then it will be convergent. Okay. So limit of log An, limit of log An. Of course, this should not be negative. And they have written in, I think An is arbitrary sequence of positive real numbers. So all An are positive. No? All An are positive. All An are positive. So you can think of and then you can write. Let me move to further questions. So many questions are there. This was, I think, this was the last question of this section. So this one, another exercise set 8.2 we have. So many of, I think, so many questions we have discussed from this now in the class. Or you have any doubt or you need to ask, you want to ask something from here. What is UN in this case? 1 upon n to the power n. No?
Yes, sir. N to the power n.
Yes, yes. So similarly, you can find out and you can use ratio test. And of course, we have discussed this in plenty in classroom. No? So some questions we have not touched that I'm going to discuss today. Which question? This question. This question, let us see. This question is something different. This is also something different. So this is 1 upon E. This, I think there is some mistake or what? Because the UN, if we are writing UN, so we can write 1 upon e to the power 1 is there. So e to the power n. Na? So denominator is clear, but in numerator 1, 4, and 27, here 2 is there. To 4 to 2 to the power 2, we can write this one, and this 27 is 3 to the power.
n आ जाएगा.
हाँ ठीक है, n to the power n. But here is it
4
okay?
to the power 4, 64 नहीं होगा sir.
There is I found this is 64 नहीं, 128 होना चाहिए ना?
Yes.
Yes, yes. So there is some mistake. Absolutely no. This is 5 to the power 5. This will come na 3125. Na? So this is UN. So what test you can apply? un is n to the power n and e to the power n, or n by e to the power n. Now, which test you can apply? Do you remember? Root test. I told you, na, when there is a power coming, so root test you can apply, or you simply can tell that this is un and you are writing n by e to the power n. Na? You can write like this, okay? So you root test un to the power 1 upon n, and then you have to compute limit. Na? So this is equals to limit, and once we raise 1 upon n to the power over un, so we are left with n by e, limit n tends to infinity. So this is going to be infinity. So whether this is convergent or divergent. Root test. Using root test, whether this is convergent or divergent. If you don't remember the test and result, how you can solve? हाँ? याद है आपको?
Divergence, sir?
डाइवर्जेंट नहीं, आप क्लियर बताइए, क्लियर बताइए आप। रूट टेस्ट क्या होता है बताओ बच्चों। रूट टेस्ट में ऐसे ही होता है, लिमिट यू एन सीरीज विद पॉजिटिव टर्म्स में यूज करते हैं, है ना, इक्वल्स टू एल। कन्वर्ज कब करता है ये?
L less than 1 पे सर।
ठीक है, और डाइवर्ज कब करेगा?
ग्रेटर देन 1।
ओके, और ये टेस्ट फेल कब होगा? इक्वल्स टू जब 1 हो जाए ना। तो ये रिजल्ट आप याद रखिए, मैं आपसे पूछ रहा हूँ कि जस्ट आई वांटेड टू नो वेदर यू रिमेंबर और नॉट। यू शुड रिमेंबर ऑल द टेस्ट, है ना, तभी आप कर पाएंगे, अदरवाइज बड़ी मुश्किल होगी। ठीक है।
यस सर।
आप आपको इसीलिए मैं क्वेश्चन करवा रहा हूँ। सिमिलर थिंग यहाँ पे भी आप यूज कर सकते हैं। यहाँ पे यूएन क्या होगा 12th क्वेश्चन में? यूएन इज log 1 0 होता है, तो ये तो n+1 हम लिख सकते हैं ना यहाँ पे। ठीक है, ओके। और न्यूमरेटर में क्या है? इतना है, और फिर पावर है here. So n equals to 1, so we are getting log this, but power is also coming, so let us put power here. Na? Is it okay? You see, log 3 is there, power 2, log 4 is there, power 3. So power is less than that of 1 less than that of log we are considering. Na? Fine.
Yes sir. Sir, 1 by log n to the power n minus 1. If we start n from 2, from 1, then log 1 by log n to the power n minus 1.
Okay. You are telling that if we are writing this if you are writing 1 upon log n plus 1 and to the power n, na? So we have to start from n equals to 1, na?
Yes sir.
N equals to 1. Okay. So this is also, कौन सा टेस्ट लगाओगे आप इस पे?
Sir, root test.
रूट टेस्ट ना? Sure.
It's a to power n sir.
आप यही यूएन इसमें है ना, यूएन यूज करेंगे, सो यू कैन यूज लिमिट un to the power 1 by n, ना? So this is going to be limit of un, तो लिमिट ऑफ क्या हो जाए 1 upon log n plus 1, है ना? This is going to be 0 and 0 is less than 1.
Yes sir.
And then तो सीरीज कैसी हो गई?
convergent.
कन्वर्जेंट होगी ना, ठीक है।
Yes.
Okay, what about this third question, number 13?
Sir, ratio test.
Ratio test, comparison test, you can try it out, no?
Yes.
Both
Yes.
cases, in both cases. Okay, one more thing, let me tell you, when your log is coming like this, okay, in power is there ना, so आप रूट टेस्ट इसमें यूज करेंगे, बट अब यहाँ पे लॉग आ रहा है, देखिए यहाँ पे आ रहा है, यहाँ पे आ रहा है, इन दिस क्वेश्चन, क्वेश्चन नंबर 15, क्वेश्चन नंबर 16, दिस क्वेश्चन एंड दिस क्वेश्चन, ऑल क्वेश्चंस ना, ऑल दिस क्वेश्चंस। सो इसमें आप जब इस तरीके से लॉग आए, सो वी हैव टू यूज इंटीग्रल टेस्ट। विच टेस्ट? इंटीग्रल टेस्ट। इंटीग्रल टेस्ट में क्या करना है, un को we need to make fx ना, this one un is what, log n divided by n square, okay, so fx हम क्या लेंगे, इसमें देखो बेटा, इंटीग्रल टेस्ट क्या कहता है, लिमिट ऑफ un शुड बी 0, फाइन, या फिर ऐसे कहते हैं कि this one, okay, this is 0 and fx should be decreasing na, then the nature of this series and this integral fx dx ना are same। अगर ये कन्वर्ज कर रहा है यानी इसकी लिमिट, इसकी वैल्यू फाइनाइट आ रही है, तो ये भी कन्वर्जेंट होगा। इफ इट हैज वैल्यू इनफाइनाइट, तो ये क्या हो जाएगा, डाइवर्जेंट हो जाएगा, है ना, याद है, ठीक है। तो इसको आप यू हैव टू कन्वर्ट log x divided by x square, fine, log x divided by x square। So one thing is that if we see here limit of un, so limit of un, that is log n divided by n square, this is the limit। अब ये infinity by infinity, fine, क्या करेंगे, एल हॉपिटल रूल, so 1 upon n above and here 2n, so this is equals to limit 1 upon 2n square, ये क्या हो गया, 0, एक कंडीशन हो गई फुलफिल। दूसरा क्या हो जाना, डिक्रीजिंग होना चाहिए। फॉर टू कंफर्म द डिक्रीजिंग वी नीड टू प्रूव दैट f डैश x इज लेस देन 0, ठीक है, ये दोनों 0 होने चाहिए, ओके।
Yes, sir.
तो ये दोनों चीजें हों और उसके बाद फिर ये इंटीग्रल आप कंप्यूट कर लेना, इंटीग्रेशन आता है ना, इंटीग्रेशन क्या करना, 1 to infinity,
Infinity.
है ना, एंड देन log x डिवाइडेड बाई x स्क्वायर dx, कर लोगे कंप्यूट ये इसकी क्या हो जाएगी, यहाँ पे अगर वैल्यू फाइनाइट आ गई, ये इतना, इफ दीज टू थिंग्स आर validated in the case, in particular cases, so we can use integral test। ये दोनों वेरीफाई करना है, देन इंटीग्रल टेस्ट लगाना है, इसकी वैल्यू फाइनाइट आई तो कन्वर्जेंट, और अगर इनफाइनाइट आ गई तो डाइवर्जेंट, ठीक है, पक्का, कोई दिक्कत नहीं। सो इन सारे क्वेश्चंस में आपको यही करना है 15 से लेकर 18 तक, ओके। हियर यहाँ पे क्या, रूट टेस्ट ना, रूट टेस्ट, व्हाट अबाउट दिस केस,
So ratio test.
रेशियो टेस्ट, वेरी गुड। व्हाट अबाउट दिस, रेशियो टेस्ट ना, यहाँ पे आप देखिए, यहाँ पे आप रेशियो टेस्ट यहाँ पे भी यूज कर सकते हैं क्योंकि 3 to the power n है ना, फाइन, तो यहाँ भी रेशियो टेस्ट आ जाएगा, यहाँ पे आप रेशियो टेस्ट ट्राई कर सकते हैं, अदरवाइज यू कैन यूज लॉग इंटीग्रल टेस्ट,
Integral
फाइन,
test.
हाँ इंटीग्रल टेस्ट आप चाहे तो यूज करिए, ठीक है, और यहाँ पे फिर कंपैरिजन और वो टेस्ट हो जाएगा, ठीक है।
Yes.
Okay. So these are, you see here, power third, 1/3 root of 8, 9, 10. You can try out some test, ratio test, comparison test. ना थोड़ी सी practice करनी पड़ेगी आपको. Now this question. This is important question. Please remember this question and solve it. So un is what? Here n log n to the power p. And in fact, this question is general form of the questions we have seen here. No? Here you see log n by n square, log n by pi n, ना? log n by n cube. ठीक है? So इन सब के general case है ये. This is important question. This is something like P series. This converges of if and only if. So what we have to do? First thing, un, limit un n tends to infinity. क्या होगा? 0 है पक्का. P is greater than 1 पे है ना. आप इसमें दो कंसीडर करेंगे. Two things we need to consider here. First thing, let P greater than 1. Okay. Then limit of un equals to 0. And also because P is greater than 1, तो ये हमेशा क्या रहेगा? डिनोमिनेटर में ही रहेगा, है ना. ये क्या है? डिक्रीजिंग भी है. फाइन. This is decreasing. This fx हम कंसीडर करेंगे fx n divided by log x to the power p. और आप चाहे तो इसको डिफरेंशिएट. This is decreasing. This is decreasing. This is x ना. This is decreasing. So we can use integral test. कैसा, कौन सा टेस्ट यूज करेंगे? इंटीग्रल टेस्ट. इंटीग्रल टेस्ट में क्या करेंगे? 1 to infinity और 1 upon x log x to the power p dx. और इसका इंटीग्रेशन करके आप देख सकते हैं ना, इंटीग्रल कर सकते हैं इसको. हेलो. बाय सब्स्टिट्यूशन टेक u इक्वल्स टू log x, है ना. फाइन. तो du क्या हो जाएगा? 1 upon x dx. You can so because you have considered that p is greater than 1, so इसके लिए इसकी वैल्यू क्या आ जाएगी? फाइनाइट वैल्यू आ जाएगी. ठीक है, लिमिटिंग केस में.
यस सर.
फाइन.
यस सर.
सो अब इसको जैसे इवेल्युएट करने के लिए यू हैव टू पुट हियर b, है ना. लिमिट क्या कर लिखेंगे? लिमिट b टेंड्स टू इंफिनिटी. ध्यान है आपको? ऐसे ही किया था ना हमने. ठीक है. तो यहाँ पे लिमिट लेंगे b टेंड्स टू इंफिनिटी और यहाँ पे ये b आ जाएगा और फिर you can complete it. Okay. So this one and another result. This one also similar question. This question log n log n to the power p. Okay. This question also you have to use integral test in these two questions also. ठीक है, कर लेंगे ना. फाइन. ध्यान रहे यहाँ पे 3 से स्टार्ट हो रहा है, यहाँ से 2 से स्टार्ट हो रहा है. The reason is behind is that n log n is defined when this one log n is defined for positive numbers, na, for positive numbers. And to make this is non-negative, and when log x becomes negative, when it becomes negative, when x becomes less than 1. ठीक है ना. इसकी वैल्यू 1 से कम हो जाती है. तो यहाँ पे अगर log सपोज वी आर राइटिंग 1 हियर, सो log 1 क्या हो जाएगा? 0 हो जाएगा. फिर यहाँ पे log है ना, तो log 0 तो डिफाइंड है नहीं. तो इसीलिए यहाँ पे क्या है, डोमेन इसका सर्च करेंगे तो इसमें n इक्वल्स टू 3 से ही स्टार्ट होगा. यू कैन यूज हियर इंटीग्रल टेस्ट. कौन सा टेस्ट यूज करेंगे? इंटीग्रल टेस्ट. सभी इस तरीके के क्वेश्चन में. और ये इन प्लीज नोट डाउन इन 32, 33, 31 they are and all these question 21, 24, this 19, this one. Here also you can use you can use comparison test. No, comparison test you can use. And this also prove that the ratio test and the root test are inconclusive for this. So you have to simply apply here the ratio test and root test. In both cases, limit you will be getting as 1. No? So in both cases, you can tell that the test is inconclusive. Fine. Okay, so this is the last thing I would like to discuss today. This is a Leibniz rule. Leibniz rule. Leibniz theorem for alternating series. Leibniz theorem for alternating series. It says that a monotonic decreasing sequence of positive numbers, then alternating series, this alternating series converges if and only if this is 0. Okay, so there are two conditions. One is the monotonic decreasing and limit is 0. So one we initially they have considered part 1. Suppose this is convergent. Okay, converge करेगा तो by necessary condition this limit un is what here, this whole thing na, this whole thing un is minus 1 to the power n plus 1 an, this should converge to 0, and this is because minus 1 to the power n plus 1 is there, so this will give us minus 1 plus 1 minus 1. This is some finite and fixed quantity. So to converge this to 0, an has to be converged to 0 no? So this this converges, so an should converge to 0. So this was the required. We assumed that this is convergent, no? Convergent. Then this should hold, fine. And then converse part. Suppose this tends to 0. This tends to 0. Now we need to prove that the given series is convergent. Okay. So to show that the series is convergent, we use the basic result. Basic result that is Cauchy criteria, na? Sn minus Sm less than epsilon. Do you remember? Greater than or equals to some natural number, na? So these n and m may be even or odd, whatever you feel like you can take them. So यहाँ पे क्या है? They have created a sequence of partial sums. First 2n terms they are taking. First, when we write like this, it means we are adding some first n terms. If we are writing 2n, it means we are adding first 2n terms. So they have added here 2n terms here, and here they have added first 2n plus 1 terms. Okay. So once we remove first 2n terms from plus 2n plus 1 terms, so we are left with this one. And because the series is decreasing, terms are decreasing, so this one is less than, this term will be less than, because the index is bigger than this one. Na? So this will be less than this. So of course this is going to be greater than or equals to 0. So this difference is going to be greater than or equals to 0. So it means that this part sequence of this 2n, this part SOPS is monotonic increasing. Sn plus 1 is greater than this one. Okay, monotonic increasing. Nah? So this index is bigger than this one. So this is monotonic increasing. And do you remember the result? A monotonic increasing sequence is convergent if and only if it is bounded above, ना? Monotonic increasing केस में bounded above होना चाहिए बेटा, ठीक है ना? Bounded below तो होगा ही ना वो, monotonic increasing है ना? ठीक है? So ये क्या, इसको क्या प्रूफ करना? We observe that this is bounded above. हमें ये प्रूफ किया ही ना. So Sn को they can write a1 minus a2 plus a3. Sn is nothing, Sn are the sum of first 2n terms of this. ठीक है? So they are writing like this. So you see here A2 is there, A3 is there. So they are grouping it and they are grouping them. So they are grouping them. So A2 and A3. This is a monotonic decreasing. So A3 will be less than A2. Now A3 will be less than A2. A5 must be less than A4 because this is monotonic decreasing. The terms are monotonic decreasing. So after all, this is positive, this is positive, this is positive, and we have seen that they are negative sign before each bracket ना. So ये सारे terms क्या है, negative है, negative है, negative है, negative है. So S2n इतना होगा, and then let us remove. Say suppose we have written x less than 2 minus 5. So ये किससे कम होगा, 2 से भी तो कम होगा ना बेटा, ठीक है, ओके है ना, इसको हटा दीजिए नेगेटिव नंबर. So all negative numbers they have removed. So we are left here A1. So this will be less than or equals to A1. So this is bounded above. So this is monotonic increasing sequence and bounded above. So monotonic plus bounded. Monotonic plus bounded means convergent. So S2n is convergent. Okay. So again, a series is, we know that a series is convergent if event terms SOPS, event terms का sequence of partial sums and odd terms का sequence of partial sums. केवल दो ही चेक करने हैं, ठीक है ना, दो चेक करने हैं, converges. So S2n is converges. Similarly, S2n plus 1 इसका sequence बनाया. So S2n plus 1 is what? S2n. S2n इसमें एक टर्म और ऐड होगा, ठीक ना, बिकॉज दिस इज ऑड. सो माइनस माइनस विल बिकम माइनस कम हियर. S2n है ना, तो इसके बाद वाला टर्म्स कौन सा आएगा, माइनस A2n प्लस 1, यही तो आएगा, है ना, ओके. So we can write S2n plus 1 equals to S2n minus this one. Now take the limit left side and then right side. We know that this is convergent, and this one we have assumed that limit of an tends to 0 na, limit of an tends to 0. So this becomes 0. So we are left with this one, and because this is convergent, so this will give us a finite number. So both this limit and this limit sequence of even SOPS, event terms SOPS and odd terms का SOPS दोनों equal हमें दे रहे हैं क्या, limit. So therefore the series is convergent. This was the proof of this theorem about alternating series, and other results are there. You can read it out, and I will try if I can get some more time. So I will spare to discuss some more results. Okay, some more exercise problems. Of course, that syllabus has been finished. And one thing I must say that I could not say in the class itself that syllabus is finished, but due to some time constraint, no. But hope to see soon in the physical classroom. So फिर भी आप लोगों को कोई दिक्कत होती है तो आप लोग मैसेज कर सकते हैं, क्वेश्चन पूछ सकते हैं, मुझे फोन कर सकते हैं, ठीक है ना, ओके.
यस सर.
आई होप डिस्कशन वाज फ्रूटफुल आप लोगों को.
यस सर, वेरी मच.
Thank you for watching this video. To stay updated, please subscribe to our YouTube channel, Cosmos Learning. Happy learning through Cosmos Learning. To watch more, click on any of these cards. Thank you once again.